Hello everyone. Today let's solve Leetcode problem number 133, clone graph. So what the question says, given a reference of a node in a connected undirected graph. So here return a deep copy clone of the graph. You can read about the deep copy as well as the shallow copy here. Lazy copy is also there. You can read what is the deep copy basically. And each node in the graph contains a value int and a list node of its neighbors. So they have just given the example over here. So test cases format, they have given for simplicity each node's value is the same as the node's index. They have clearly mentioned that it is one index, right? So this one we have to keep in our head. Next thing is, for example, first node with the val 1, the second node with the val 2 and so on. The graph is represented in the test case using the adjacency list. They have given the graph is represented in the test case using the adjacency list, right? So we will just see it in the form of graph, and it will be easy to understand. An adjacency list is a collection of unordered lists used to represent a finite graph they have given. So an adjacency list is a collection of unordered lists used to represent a finite graph. So each list describes the set of neighbors of a node in the graph, right? So what they have mentioned, each list describes the set of neighbors of a node in the graph. This is fine. The given node will always be the first node with value 1. So for the example they have taken, for the given node will always be the first node with value 1. You must return the copy of the given node as the reference to the clone graph. This is fine, right? Let's look at the example 1. So here the graph is 1, 2, 3, 4. They have mentioned this one as original graph. We cannot return the same graph they have shown. So we cannot return the exact same graph they have shown. So we have to return the graph exact same node values, but we have to return the new node. As far as I know, we have to return the new nodes, right? So here this looks like a clone. The nodes are new. So yeah, graph looks the same. So this is what we want. The output. So the output has to be, we have to return the new nodes with the exact same value as the original graph, right? So this works. The last one is here. The graph, they say the graph is messed up because the values here are different. So this has to be 2 here, right? 2 and 3. Values are interchanged here. So this is also wrong. So this has to be in this way. So for this one output, they have given the output in the form of adjacency list, right? So here they have mentioned an adjacency list is the collection of unordered lists used to represent a finite graph. Each list describes the set of neighbors of a node in the graph. Basically, they are mentioning the set of neighbors of a node in the graph. For 1, the set of neighbors they have mentioned. For 2, the set of neighbors they have mentioned. For 3, the set of neighbors they have mentioned. For 4, the set of neighbors they have mentioned. So the output will be 2, 4, 1, 3, 2, 4. Same thing, right? So let's see. Let's try to understand this. So let's consider this one. Example 1, right? So here, let's take this example itself, the first example. So we have 1, 2, this one will be 4, and this one will be 3. So what is the adjacent list for this? So 1, basically we are saying first we will consider this node. So what is the adjacency list? So we will see what are all the nodes the 1 is connected to. Basically this is connected to 2 and this is connected to 4. So for this one, 2 and 4, right? For 2 is connected to 3, as well as 2 is connected to 1 and 2 is connected to 3. So this one will be 1, 3, right? This one will be 1 and 3. Next, let's consider 3. So 3 is considered to 2 and 3 is connected to 2 and 3 is connected to 4. So it will be 2 and 4, right? Finally, we will consider 4. 4 is connected to 1 and 4 is connected to 3. The node 4 is connected to 1 and 4 is connected to 3. it will be 1, 3. So the total, the adjacency list is 2, 4, 1, 3. This one 2, 4, 1, 3. 1, 3, 2, 4, and finally 1, 3. That's what here we have got the input. So the output we have to return the new nodes that will be exactly same as the original nodes, right? That's what original graph. So that's what 2, 4, 1, 3, 2, 4, 1, 3. We have got the output. So what we can do is first we will check if the node 1 is visited. This one we will check first if the node 1 is visited. So just give me a second. Just give me a second. First, let's go with the base case first. So if the input node is null, right? So suppose we don't have anything, we don't have any input. So suppose if the input node is null, then we will return null. So we don't have anything. Suppose just ignore this for now. We don't have anything. Suppose the input node is completely null, then we will return null. Basically to handle the empty graphs, right? If we don't have any value, then to handle the empty graph, we will return null. That will be the base case. So second one, what we will do, second step, we'll carry on with the DFS with memoization, right? So what we will do, we will keep track of the visited nodes. Why we will keep track of the visited nodes? Just to avoid the recloning, right? So also to handle the cycles in the graph. So these two things we have to keep in head. So we will keep track of the particular node after it gets visited to avoid recloning as well as to handle the cycles in the graph. We will start from the node, first one, input node for each node. So if it's not already cloned, we will be creating the new node with the same value. So suppose if I come here, so suppose we are visiting this node 1. So I'll just mark this one, new node 1. I'll just take N1 in this case. So I'll just take N1 and I'll mark this one visited because we have already visited this node, right? So same goes with the node 2. When I come here, I'll just mark this one as node 2, new node 2. This is not visited. Basically, this is not already visited, right? So I'll mark this one, new node 2, and this one is visited now. The third one, same thing we are doing. Well, I come to the third node, I'll just mark this one visited. This is not already visited, not visited already, sorry. And this, I'll keep this one as new node 3, and this will be visited now. Same goes with the fourth one. While I visit the fourth one, I'll just mark this one visited, and let's take this one, suppose new node 4. That's what we will be doing. Suppose if we carry on with this next again, then it will come to 1, and this is already visited, right? It would form a cycle. So this is already visited. We'll be ignoring this one once visited, right? So this will be helpful. Next, what we will do, we will recursively clone all its neighbors. So I showed you the individual step, right? What we will be doing. We will recursively clone all its neighbors and link them to the new node, right? So while we link them to the new node, what output we will get? We'll be displaying the adjacent list, but in this case, I'll just show the same thing. While this is this one, while we visit, so we will be creating the new node, that is 1. This is not already visited, right? First time when we visit, this will be 1. Next time, this is not visited, so we will create the new node and we will be displaying the value of the node within this node, nothing but 2. Same goes with 3 and same goes with 4 as well. So the output will be same with the new nodes, nothing but this. We will call it as the clone graph. That's what they have said in the question as well. So that's what they have shown here. So finally what we will do, we will return the clone graph. Nothing but the clone graph is return basically. That's what we have done here, preserving the original graph structure. So the same thing we have got here. Let me delete this. let's see how can we implement this in code. So I'll just come here. So initially what I'll do, as I've said, if the input node is null, this was the base case, right? If the input node is null, then we will return null, because there is no graph to clone, right? So if the input node is null, then we will return null. This is one thing. Next, we will define the DFS function to clone nodes recursively. So I showed you in the example. So I'll just take this one, const DFS, just the function name. Just take two parameters. One is node and one is visit. So first what we'll do, if the node is already visited or if the node is already cloned, we will return the clone node. Simple. We'll be making use of the if condition for this. I'll just give visited dot has node, then we will return visited dot get of node. This is one thing. Next, what we'll do, we will create a new node with the same value as the current node. So as I've said, so here we shouldn't return the same graph, right? That's shown here. Also I shown in the example that I took. So we should not return the exact same graph. So we should be returning the new values with the same value, right? So for that purpose, what we will be doing, we will be creating the node with the same value as the current node. How can we do that? I'll just take the variable name, new node, in my case, sorry. Yeah, new node. New node of value of the. Next, what we'll do, we will be storing this new node in the visited map. So visit means we are marking this one as visited. I showed you in the example, right? We will be storing this new node in the visited map to avoid the infinite loop or the cycle, right? So for that one, what I'll do, let's consider visited dot. We'll be making use of set, right? Simple node and new node. So next, we will recursively clone all the neighbors of the current node. We'll carry on with the further steps. That's what I'm saying in the simple words. So let's make use of the for loop. Neighbor. Oh, we have made use of node.neighbor, right? It will be node.neighbors. And neighbors, new node, neighbors. We will push, we'll be making use of the recursive function for this. What we'll be pushing, neighbor, and what are all the what are all the nodes that we have visited. For 1, it will be 2 and 4. For 2, it will be 3 and 1. For 3, it will be 2 and 4. And for 4, finally, it will be 1 and 3. So how can we write this? Let's make use of the recursive function, nothing but DFS of 2 parameters that we have taken here. One is neighbor and visited. So neighbor as well as visited. So this is fine. Finally, what we'll do, we'll return the clone node. So we have to return the clone node itself, right? So new node, this will be. Here, what we'll do, we'll start the DFS with the original node. We will start the DFS with the original node in this case, and an empty map to keep track of the visited node. So we are making use of the map to keep track of the visited nodes. So whether it is already, this node is already visited or not. For that one, we will be making use of, we made use of the this one empty map, and we initially started with this node with the with the DFS, right? So that's what we will be writing here. So return DFS of node as well as new map. So this is simple. I'll just let me format the code and hit the submit. So this is correct, right? This is working absolutely fine. So what would be the time complexity and the space complexity? The time complexity, overall time complexity would be big O of V plus E. So we know that V, just give me a second. Yeah. We know that each vertex V and the edge E. So this thing, edge E, we are visiting the vertex V and the edge E exactly once, right? So the time complexity will be linear in the terms of nodes and edges. So overall time complexity would be big of V plus E. This is simple. Space complexity would be big of V. Why the space complexity would be big of V? Because the number of vertices V basically just give me a second. We are making use of the recursion stack, right? So here, this one, if you can see, we are making use of the recursion stack. That's the reason the space complexity would be big O of V. So I'll just come here. So time complexity and just give big O of V plus E, vertices and edges, and the overall space complexity would be big O of. So this is it. I'll just comment this one. So yeah, this is it. Thanks for watching, guys.